So we'll start talking about the half wave rectifier. Uh, we talked about the full wave rectifier in the last class, so we will go over an experiment related to the half wave rectifier to start off with, and then we will talk about voltage limitation, uh, do an experiment on that. Then we'll do item number 3 on this list, which is going to focus on light sensing and generation, LEDs and photodetectors, and then we will introduce the concept of Zener diodes, but we will finish it on Thursday of this week. So let's start talking about rectifiers. When we left off in the last class, we were, I believe, looking at the concept of rectifier. Let's see here. Um, so my experiment 8 is right there. Okay, so I hope you are able to see this on the screen. This is where we left off in the last class. The half wave rectifier circuit is shown in figure B-1. This circuit uses one diode and one resistor of value 10 kilo ohms. And we talked about how we can add a capacitor in parallel with the resistor to smooth the rectified output. And depending on the value of the capacitor chosen, we may have uh, uh, if we choose a big value of the capacitor, then we follow the red line where the discharge is slower, and hence we reduce the ripple voltage, which is what we desire. And then if we have a small capacitor, we will follow the blue line more or less, where the ripple voltage will be larger, which is not a very good rectified DC output. Um, so let's see. We are going to take a look at adding the capacitor to do a rectification. But if we set up the circuit as shown in figure B-1, the first thing that we will notice is, given an input sinusoid or an input triangular wave, if we measure the resistance, if we measure the voltage across resistor R2, then we should observe something that is similar to the red line on this graph. So that's the voltage across the resistor. Now notice there is going to be a little difference between the red and the black, because we are going to need about 0.7 volts to turn on the diode. So that's going to function as the threshold for the diode. So whatever you give over here, source voltage minus 0.7 for the diode, that is going to be available across the resistor R2. Today's class, it is going to be jumping back and forth between experiments, waveforms, analog discovery, and then we will switch back as and when necessary to the concept discussion. So let's start with the experiment right away. So we are going to set up this half wave rectifier as shown in figure B-1. Over here it says uh, at the wave gen have a triangular wave input with a 1 kilohertz frequency and 5 volts amplitude, and later on we actually need to gather results for a sine wave input. We will start with triangle and then we will go to the sine wave. Notice I have followed a pattern in experiment 8 where whatever is highlighted with blue is essentially the circuit building component, which I will be doing, and then whatever is highlighted in yellow, for example, over here, whatever is highlighted in yellow, this is a PSpice component to experiment 8, which you guys will be working by yourselves. So let me go back here and let's set up figure B-1. Very simple. It's going to be one diode, one resistor, and it shouldn't take too much time. We will have, let's see, we will have channel 1 measuring the wave gen, and then we will have channel 2 measuring the voltage across resistor R2. So let's quickly set this up. So what I can do here is I can switch on my uh, video, and let's take a look at the components that I will need for this. So I will need a resistor, I will need a diode, and then I will need a few more items. This is a smoothing capacitor, so a 4.7 microfarad capacitor right there, um, and a few wires for measurement. So I think we are good in terms of the circuit. So not too many things involved here. I think this needs to be flipped. Okay, that's actually okay. Then I'm going to start off with looking at the diagram. I have wave gen coming in, so I have a yellow wire. So I'm going to connect my yellow wave gen. Okay, that gives me yellow, followed by a diode with the positive terminal, the anode facing the wave gen. I've done that. And then I have a resistor connected to ground of value 10k. Actually, you know what, let me just move it one up so that this is a little bit better in terms of organization. And then I can connect the ground terminal right there, goes to ground. What else do I need? I need a black wire to connect to ground. um, Hopefully I can find okay. Then I need two channels. Both the scope 1 negative and scope 2 negative need to be connected to ground. I have done that externally, so I've connected blue stripe to black and orange stripe to black outside of my proto board. I'm not going to have too many wires here. So essentially what I need to connect is orange and blue, which is for 1 plus and 2 plus. So orange wire needs to connect to wavegen, so that's measuring the source, triangle, sinusoid, whatever it might be, and the other blue wire needs to be connected to measure the voltage across the resistor. So that's going to be at the common node between the diode and 10k resistor. So let me connect that to the blue wire, which is right here. Okay, so connected ground, everything looks in good shape here. So I believe I'm ready to, I can zoom in to show you guys things a little bit better, maybe. But essentially I'm ready to start waveforms here. So what I'll do is minimize my, or I can just quickly do this. I'm starting waveforms here. Detect the board, sure. Do I need scope? Yes. Do I need wave gen? Yes. And do I need supplies? Not right now. So what I need to do over here is give wavegen a triangle wave of frequency 1 kilohertz and amplitude of 5 volts, and I'm going to make it a little bit thicker so that it's easier to see. I'm going to run wavegen and I'm going to go to scope. Because I have a frequency of 1 kilohertz, I'm going to set my time division to 200 microseconds per division so that I have two full time periods. Range, because I'm looking at 5 volt triangle wave, peak to peak it's going to be 10 volts. So I'm going to choose this as 2 volts per division for channel 1, 2 volts per division for channel 2, and then I think I'm okay to run. So the moment I start the scope, I can see two lines, channel 1 and channel 2. I'm going to remove noise on both of them, and I'm going to make the plot width thicker. So for example, I can go to 3 here, and the blue line is the rectified output, I should say half wave rectified output, and clearly you can see that the average of the orange line, the source, is a 0, but the average or the mean value of the blue line is positive. And that's the first step uh, to convert an AC signal to a DC signal. Move the average up, and then if we are able to use a smoothing capacitor, it will look more and more like a DC voltage. So that's essentially step number one. Let's see, I'm going to minimize this and go back to my circuit. Over here it says I need to do it for uh, a triangle wave with 1 kilohertz frequency, which we have done. And then once we are through with this, we can actually move on to the next part. So what we can do here is, um, so at this point, actually the students have an option to plot using analog discovery software, which is waveforms, or in Excel or in MATLAB. So Excel is probably not a very good choice here. Analog discovery waveforms or MATLAB is appropriate. So just so that you guys get to vote on this, I'm going to start a poll and I hope you guys participate. So I'm going to see what your preference is going to be. So I'm going to start a poll here and I'm going to open a poll from desktop. See this? Okay. And I don't think you guys need the full 5 minutes to do this. So maybe 2 minutes is plenty. And if you guys are ready to take a poll, um, how do I open? Yeah, open. So now you guys should be able to take a poll here. All right. So responses have started coming in. That's really good news. All right. 1 more minute remaining. So people who need to get their responses in, if you guys can just so I love that both of the options are competing with each other. Okay. Uh, WebEx gives you it's about 20 seconds to kind of do the last minute thing, or I should say last second thing. Okay, so we have a winner. Waveforms got 12 out of 26 votes and MATLAB got 10 out of 26 votes. So MATLAB lost just by a couple. Um, my vote actually goes for MATLAB, so I guess we are 12 versus 11. So that's okay. I'm going to provide the output in waveforms, but just in case anybody wants to play around with it in MATLAB, I will save that CSV file as well. My main motivation for this was to uh, test this polling feature. So I think it went well. Okay. Let's see. What do I hear you. We can make it up. We can make it up. We will save it. Let's see. File save as. I can save like the data, and I can. Derek says no. Yeah, figure B10. No, this is not B10. This is B8. The first one. Okay. All right. So if I share the data with you, I hope you guys can import it into MATLAB and sketch things over there. All right, let's move on here. Thanks for participating. What do we have next? So if I bring up my window here, let's take a look at what's next. So we talked about the full wave rectifier. There's no experiment on that, so we don't we are not going to really do that. But we talked about how it works and how it is better than the half wave rectifier, even though it requires three more diodes. It will perform really well. So let's keep going here. On page This is 11. On page 11, all the items that are listed are uh, capture PSpice related. So you guys are going to work on that. The good news with this is it's not going to be too long. It's a few components at a time, and the instructions are reasonably detailed, so that you guys can follow that to run those simulations. But make a note that later on we will take some experimental data, so data from the plots, and then we will try to uh, put those experimental data points on PSpice generated plots. So you guys can do that. I will give you guys the data points. You will incorporate them into your PSpice results. So let's move on here. On page number 12, the entire page is dedicated to experiments, and this is hardware implementation of the rectifier. And we'll start off with B7. In figure B-7, it is the exact same circuit diagram that we have hooked up over here. So a diode and a resistor of value 10K. The only difference here is that we are moving to a sinusoidal signal with a 100 hertz frequency. So just the shape of the signal is going to change, and the frequency is going to change. And then we will do the same thing. We will do this in waveforms, and then I will share the results. Okay, so let me bring up waveforms here. We had the triangle wave setup. We are going to change that using WaveGen to a sine waveform. Don't need frequency of 1 kilohertz. I need a frequency of 100 hertz. So we are going slower in this case. Come back to scope and run it. Now, of course, because we made things slower, we are going to have to adjust our time scale. So from 200 microseconds per division, I'm going to jump to 2 milliseconds per division. So that way I will be able to see two time periods. So that's my half wave rectified output for a sine wave input. And in theory, the reasoning is the same. It's getting, the average is going up. We are essentially eliminating the negative half cycles because no current flows through the diode when they are negative, when it is in the reverse biased region. So the underlying concepts are very similar. It's just that the shape of the graph is sinusoidal instead of a triangle wave. Okay. So that's our analog discovery plot. And I'm also going to quickly do a export for MATLAB so that you guys can use that if you wish. So that is going to be, I believe, figure B-7, and I can say 7A. Earlier one was figure B1. I think this, okay, save it, sure. Okay, let's see if we are done with B7, and because I have a few items to work on, I'm kind of maintaining a steady pace here. So if you guys need me to slow down or answer a question, feel free to type it in the chat box. Next, figure B-8 actually is the more interesting graph, because now we are going to add a smoothing capacitor, and the value of the capacitor chosen here is 4.7 micro, and we'll actually change the value of the capacitor a little bit to see what the effect of that is going to be, but that is coming up later. Right now we just add the capacitor to the circuit. So C2 is in parallel with R2. I will go to waveforms, temporarily stop my wave gen, and add my capacitor between, so exactly across the two ends. So let me see, maybe I can do that, and then hopefully you guys are able to see the connections better. Maybe. Okay. So with the let's try to see how this waveforms window changes when we have a smoothing capacitor. So all I need to do is start wavegain again, start scope again, and the moment I do that, you can see that there is a smoothing effect. So basically it charges up to where it reaches the peak, and once it reaches the peak and the input signal is going down, the capacitor C2 is going to discharge, but it's going to discharge slowly, depending on the time constant established by R2 and C2. So this goes down until the next charging cycle comes in, which is going to be only the positive half cycle, because we have already eliminated the negative half cycles. So that's your smoothing with the 4.7 microfarad capacitor, and this is for a frequency of 100 hertz. So let's see, we can play around with the frequency to keep changing the effect. So for example, what if I increased the frequency of my wave gen? Essentially, if this peak, my second peak, came in much sooner, what is going to happen? Well, I'm going to be stopping the discharge of the capacitor sooner, which means that my ripple voltage is going to be less. So that's going to be something good in terms of the DC conversion. So if I increase the frequency, this guy comes up here and I stop it right there, which means the ripple, peak to peak ripple, is going to be smaller. And I will observe that by increasing the frequency from 100 hertz to, for example, 1 kilohertz. And on the other side, I can reduce the frequency, so meaning that I can spread these sinusoidal peaks apart further, and by doing that I will be allowing the capacitor C2 to discharge for a longer time, meaning the ripple voltage will be bigger in that case. So a poor DC rectified output, and we'll see both of these phenomena play out by changing the frequencies. But before I do that, I'm going to export my data. This is, I believe, B8. So actually this is B8, and I'm going to name it figure B-8A. Instead, not A, I'm going to say underscore 100 hertz, because this is when the input wavegain frequency is 100 hertz. Okay, so I'm going to save that, and you will have that when you need. Okay, um, let's see, what do I do now? Figure B dash 8 is done. Right. So I can vary the frequency. So I'm going to be doing the last part here. And so the last item says vary the frequency of the function generator um, and try to see what the effect is on the rectified output. And we will also change the capacitor from 4.7 microfarad to 100 microfarad capacitor and see what the effect is going to be. So we'll do both of them right now. Okay, so let's see. Circuit is the same. Going to go back to WaveGen. I already did this one with the smoothing capacitor. Going to go back to WaveGen and let's say we make it faster. I'm going to change the frequency of the sine wave to 1 kilohertz. Same amplitude, same type. Go back to scope, run it, and as you can see, because I increased the frequency by 10 times, and I did not change the y-axis range or the x-axis range at all. These are the same divisions or milliseconds per division and volt per division ranges as they were earlier. I've increased the frequency 10 times, so I have 2 cycles, 20 cycles now instead of 2 cycles. So that makes sense. But if I was just trying to compare the effectiveness of my DC, in that case, I would, if I can leave my Y ranges, meaning volts per division, as is, but instead of looking at 2 milliseconds per division, I look at say 200 microseconds per division. So this is, I'm essentially zooming in only on the x-axis. I'm leaving the volts per division on the y-axis as is. So this is probably going to be a better comparison as long as input frequency, impact of input frequency on ripple voltage is concerned. So clearly, leaving everything else the same, if you increase the wavegen frequency, your ripple voltage goes down, as is demonstrated using waveforms here. So I'm also going to export this one as a CSV for you to use. So this one is going to be 1K instead of 100 Hertz, and it's corresponding to figure B8 itself. So save that, sure. Now let's see what happens if we go the other way. So let's go back to WaveGen here. Instead of going up to 1 kilohertz from 100 hertz, let's go down to 10 hertz from 100 hertz. Still the same amplitude, still the same sine wave. Come back to scope, run it, and now things have become very, very slow. So now we are going to have to adjust our time base, zoom out a little bit. So if we were at 200 microseconds per division, we would need to go to 2 milliseconds per division for 100 hertz. We would need to go to 20 milliseconds per division for 10 hertz. So now clearly, again, we are leaving the y axis the same, so that we are not trying to exaggerate the ripple voltage by zooming in on the y-axis. We are leaving that as is. We have just been changing the x-axis. So now that we have changed it to 10 hertz, we are allowing that capacitor to discharge for a longer time. And in fact, you can see that this is looking more and more like an exponential decay. Earlier, we were looking at it in like almost a linear decay because the points were pretty close to each other. Now that we are extending that time, we are able to see that it's an exponential discharge. So the ripple voltage over here is very pronounced. It's pretty big. So this is not a very good way to convert an AC to DC. But there's one key thing here. Let me save this first, and then I will do the rest before I forget. Yes, I know it. I need to rename that guy to figure B1. Yes, I am aware. This is figure B8, but not 100 hertz. this guy is going to be 10 hertz. Okay. So bigger ripple voltage there. I've saved the graphs. What else do I need to do? All right. So to see the effect of a good AC to DC conversion, we probably don't want to ask the user to change the frequency, right? So that's probably not a good design. We usually will not have the choice of changing the frequency. However, we will have a choice to actually change the capacitor and make it to a bigger capacitor. So for example, what I'm going to do here is to stop wave gen, I'm going to remove this 4.7 microfarad capacitor and go back to or change it to a 100 microfarad capacitor instead. So between the same 2 points, so it is exactly in parallel with the 10 kilo ohm resistor here, but now it's a bigger capacitor in this case. And just so that we compare consistently, I'm going to run this wavegen at 100 hertz. That's my reference, 100. I'm going up from there, I'm going down from there, but 100 hertz is my baseline. So if I choose 100 hertz, sine wave, sure, everything is okay, let's run it. And if I go back to scope and run it, now you see we are seeing a lot more frequencies, but I'm going to adjust my uh, scale here to 2 milliseconds per division. And as you can see clearly, when we had 100 hertz, we were able to, earlier with the 4.7 microfarad capacitor, we were able to see some ripple, but with a 100 microfarad capacitor with the same wavegain frequency of 100 hertz, we almost see no ripple voltage. It's very close to perfect DC conversion here. So I'm going to also save this and save, and this is going to be figure B8. However, this is 100 hertz, and I'm also going to say this is 100 UF. So that's there. Save it. Sure. Okay. So I hope that was helpful to you guys. What we did is a half wave rectifier for a sinusoid. We kept changing, we played with the input frequency, we played with the capacitor values and saw what a good AC to DC conversion looks like. So essentially what a good rectification should look like. Okay, so at this moment we can take a few questions. Okay. So a student has let me know that my voice is breaking up. Uh, do most of you feel that way, or uh, what's going on? Okay. Uh, okay. Well, on my end, uh, there's once in a while, not all the time. In the past 5 minutes, it's not terrible. Um, okay, so let's do this way. Since I do not have anything to change on my end, uh, there's nothing really that I can do at the moment, apart from just calling the internet service provider, and I don't think even they can help on such short notice. So what we'll do is this: if you guys miss anything, any explanation or any words, you will have just type it in the chat box. Let me know, and I can repeat what I've said. So just use the chat box to get some clarification. Okay, let's see, what else do we need to do? We are done with the half wave rectifier. I'm going to next work on the limiter, voltage limiting application. I can switch off it and minimize, go back. Okay, so that is not good. All right, please cooperate. All right, okay. Um, so we are done with figure B-8. Let's move on to the next part. Figure B-9 is a PSpice simulation. So I hope you guys will work on that. And figure B-10 now is the hardware implementation for a limiter. So before we talk about a limiter, what I'll do is quickly go through the motivation for a limiter. So let's suppose there is a circuit here. I'm going to put, say for example, a system which is able to accept an input to do something on it and give an output out. However, let us say that if it was required that we supply an input voltage that ranges between -1 to 1 volt plus 1. So the limit is that this system can only accept voltages that are between -1 to +1 volt. So if that is the case, and let us assume that our actual voltage is like this. Let us say we had, we can do this actually. Okay, so let's some arbitrary shape which sort of looks like a triangular wave, but I'm going up and down. I know that there is a lag, so this will appear in a few seconds. There we go. So this is time here, and this is voltage. Okay, so I'm going to cut the middleman out. All right, guys, I hope you guys are able to simply look at the other screen if you can. So it may appear on this guy, but this will happen first. So I'm going to do both, whichever comes to you more conveniently. You can use that. So what I've done is I've sketched out a time domain waveform which is looking like a triangular wave. However, maybe I'll say this guy over here, the highest voltage, let's say over here is uh, 5 volts. Actually, I don't even need that. Let's say this is 1 volt, and similarly this is -1 volt, for example. So if those two are 1 and -1, and if I was trying to do a satisfaction on this requirement, so if I was trying to do a fit so that my inputs only fall in the region of -1 to 1 volt, I have two choices, simple choices. I have two of them. One is I can squeeze my waveform such that this falls at that point and this guy falls on this point. So essentially I can do a compression exercise on the red waveform, and I will be able to satisfy the design requirement. Or in places where I don't really care about all the information, I may choose to do something else. I may simply choose to do this. Essentially, I could say chop off everything beyond the values -1 and 1. So essentially, limit using a voltage limiter. So by doing that, I will be able to satisfy the design requirement. However, the problem with that is that I'm going to lose out on that information. So I can do it only if I'm okay with losing out on that information. But this is something that we can accomplish by using the diodes. So to talk about that, I'm going to take up the experiment window itself, because this is becoming very tedious. Go down in my experiment write-up and take a look at the limiter discussion, which is on page 13 of the experiment write-up. And if you take a look there, what you have is figure B-10 has wavegen connected to a resistor of value 1K, and there are two diodes that are parallel to each other over there, and those diodes are functioning as such. D1 is going to be forward biased for positive voltages of wavegen, and D2 will be forward biased for negative voltages of wavegen. And because of that, if we measure 2 plus and 2 minus is across both the diodes, if we measure at those 2 points, we will be able to see positive voltages limited to one diode threshold voltage, which is 0.7. And on the negative side, similarly, we will be able to see negative voltages that will get limited to 0.7 on the negative side. So negative 0.7 because of D2. Now clearly, if you want that voltage to not get limited to plus and minus 0.7, but instead want to limit to, for example, plus 2.1 and negative 1.4, then we can have three diodes facing down over here and two diodes facing up over there. This is exactly similar to what we talked about in the previous lecture. I don't know if you guys remember, the end of the last lecture we talked about that example. So where our limiting was different on different sides. So that's the general concept over here. Now we will look at the circuit and work through the experiment. So I'm going to bring back my things. I'm going to remove a few. I hope my wave gen is off. Yes, it is. I need wave gen. Okay, then I need a 1 kilo ohm resistor, so I'm going to replace. So I'm going to put the diode by the side. Actually, I need two diodes, so I'm going to bring in another one here. Don't need 10k, don't need 100 micros, so I'll take those out. Put a 1 kilo ohm resistor between 1 plus and 2 plus. So that goes right there. Then I have two diodes that are in parallel. So I'm going to place one guy facing right and one guy facing left between those same 2 points. Facing meaning the negative is on left and negative is on right. So the black ring for the bottom LED, for the bottom one, is pointing this way or pointing right, and I don't know, I'm pretty sure you can't see it very clearly, but the way I have connected them, the top diode, the black ring is facing left, the bottom diode, the black ring or the negative terminal, is facing right. So that's how I have the two set up. So I've got resistor, I've got those two, then I need 2 minus to go to ground. That's already connected externally, so that's fine. And I need the ground terminal right there. So I'm going to move the ground terminal to that row and zoom out a bit to give you the complete picture. So yellow, wave gen, same point, we have the resistor 1K, we are measuring using channel 1. The node between the diodes and the resistor, over there we have two diodes that are pointing in opposite directions, a resistor and H2 plus, and then we have ground, positive of one diode, negative of one diode over there. So that's how we have set it up, and I would expect the output to be limited to plus and minus 0.7 volts in this case. So we are asked to set it up as 100 hertz, 5 volts sinusoidal input. Let's go ahead and do that. 100 hertz, 5 volt sinusoidal input. That's exactly what we have set it up as. And if I run it here and I run it there, we can see that the output got limited to plus and minus very close to 0.7. So I can maybe make things a little bit better by looking at this. So now we have 1 volt per division. So if this is 0, that is 1. This is sort of stopping at 0.7 volts. When I provide this data to you, I will mark the data points, or I will just give you guys a table of data points so you can extract the information from there. And for those of you who are interested in the MATLAB plots, I'm going to export it as a CSV file and give it to you that way so you can take a look. So this is figure B-10, I believe. So I'm going to save that. Okay. So things got limited. That's exactly what I was hoping to see. Go down. Let's see. Okay, we are done with that. This is what I was talking about earlier. Record at least 5 experimental voltages and add them to your PSpice output. So the PSpice output will be obtained by when you go through the figure B-9, and on that result window or on that result plot, you will take 5 data points from the experimental data and then you will put it over there. I'm going to give you guys the points, use them in your plots on PSpice plots. Okay, so next question over here is, what is the effect of altering the amplitude of your circuit? So of the wavegen, right? So we are trying to change the sinusoidal input voltage. Instead of making it 5 volt amplitude, we are going to change it to 2 volts amplitude and see what is going to change. My guess is it is not going to change much. It is simply going to be still limiting the same values. So if I go back here, amplitude was 5, now amplitude is 2. We are still running. Now we are running. So now it's showing us, maybe we can take a look at this. So it is still limiting to 0.7 plus and minus 0.7 volts, but here you are able to look at it in a better fashion because we have sort of squeezed the input and then did the hard clipping. It's called hard clipping because we are essentially losing the information. So it's a hard clip as opposed to a soft clip. A soft clipping is going to be sort of squeezing things down to fit them into a range. Okay, so that's well, I need to save this data as well so that you guys can export, save. This is underscore 2 volts. Okay, so the last series of questions is, we need to alter the circuit to limit only in one direction. Well, let us see. If you want to limit it only in the positive direction, what should we do? The circuit says we have two diodes. If I were to remove D2, then I will essentially be limiting it in the positive direction. So as simple as removing it, D2 will do the job. So let's do that. Go back to waveforms, have it running, and remove D2. D2 is the one that is up here. So I'm going to remove that guy, put it by the side, and run it again. And now you can see that the input waveform is only getting clipped on the positive side. On the negative side, it works absolutely the same way as the input. So it's following the input on the negative side, it is getting clipped on the positive side. Over here, remove one of the diodes. What part of the signal is being limited? You know that. Take a picture of the output. Sure. File, export. Yeah. So this is, oh, this is 2 volts, but that's fine. For 2 volts is the same thing as 5 volts. So figure B10, 2 volts. Remove D2. Save. Sure. Okay. So we'll save that. Let's go back to our circuit here. It did that. Now reverse the polarity of the remaining diode, essentially turn it around. What signal will be limited now? Well, if we flip it, then instead of limiting the positive half cycles of the sinusoidal input, we will be limiting the negative half cycles of the sinusoidal input. On the positive side, it will essentially follow the input signal. So let us stop wavegen, temporarily take out the diode, flip it, put it back in, and run wavegen, run scope, and clearly you can see that this essentially flipped everything. So now the limiting is happening at negative 0.7, while on the positive side it follows the input signal. Okay, I don't think for this we need to do save of the plot, do we? What part is just a question. So by using the information that is provided, you guys should be able to answer that question. Okay, so I think that is it in terms of limiting. So I will stop the recording here.